So first I want to thank everybody for coming, and I wanted to thank the IE for giving me the opportunity to talk. Strictly speaking, John Bowers' name should be up here with mine because a lot of this work was done in collaboration with John. So I will basically give you a motivation of why we're trying to do this, a system description. I'll talk a little bit about the circuits, but I'll probably go a little bit fast because it's not, I'm trying to keep the talk very sort of high level, not necessarily very detailed. If you have any questions later on, feel free to ask me. I'll talk a little bit about our approach, which is wafer-scale integration, and what we plan to do in the future. So here's the problem. So if you look at the growth of data consumption, so if you look at the year between 2009 to 2020, if you look at voice, it fairly stays constant over this period, and this is terabytes per year. But if you look at things like peer-to-peer or internet video and mobile data, they basically start to go up much faster. And as to be expected, as we start to create more of these apps and more of these kinds of things that everybody wants to use, then we would expect this kind of trend. And if you look at the power consumptions or the relative energy consumption of data centers relative to, say, mobile radio or the L3 backbone, in 2009, it was pretty comparable to the access. As we go up to 2015, it starts to take over substantially from the rest of the other drivers. So let's look at a data center carbon footprint. So if you look at carbon dioxide emission as by industry, so the data centers like 0.2, airlines 0.6, shipyards, steel plants, this would be expected. This is sort of the trend you would expect. If you look at it by country, data centers are about 80 megatons CO2 a year. Argentina is only 142 as a whole country. So data centers are starting to produce a lot of carbon dioxide, and it's comparable to like small countries. And if you look at the emissions from data center, and this is the cumulative compound annual growth rate, in 2007 it was 80, and in 2020 it's projected to be 340, which is a huge spike. If you look at the breakdown of the power consumption, so a lot of it is actually in the computing. It's 580 kilowatts. The cooling power is another huge driver of the power consumption in this whole pie. One of the most interesting things is what's called the Cascade Effect. So if you save 1 watt in a processor, as it starts to go down, like the DC-DC converter, which is the power, then you have AC to DC. So this is regulation, DC-DC regulation. This is outlet to DC converters. Then you have the power distribution, the uninterrupted power supply, cooling, and then the building. So if you cascade this all the way through, even though you're saving only 1 watt here, by the time you translate it down, it gets to 2.84 watts. So it actually is a very good thing to be saving a lot of power up front at the computational level. So this is something that we should be trying to do because the savings are tremendous. So if you look at data center switches, on the other hand, if you between 2006 and 2010, this is sort of the trend for a switch router based on the research and design that people have been doing. Whereas if you look at the actual demand on the data center, it grows much, much faster than the rate at which the switch and the routers are growing. And it's outpacing it by more than 10x, which is actually a problem. So where are the opportunities? So if you look at the sort of energy consumption and what kind of technology will give what kind of improvement over the baseline, which is like 60 billion kilowatt hours, as pointed in 2006, the chip level gives you 50%. And if you keep going down, if you look at the biggest bang for the buck, it's nanoelectronic circuitry, which is basically making more miniature devices, which actually gives you better power savings at the processor, and switching to all optical networks, which actually helps you with the data rate and the power dissipation. So this is where the big opportunities are, which is the all optical network. Now, currently everything is electrical, optical, back to electrical. So it's not an all optical system. So a lot of the energy loss and the conversion is actually where the savings can be achieved. So if you look at an electronic switch, it gives you these characteristics. It has full IP routing. It has enhanced security, and it's scalable because you can make parallel ones. If you look at the Cisco CRS-3, which is one of the most popular switch routers that are used in data centers, it does 4.48 terabytes per second, and it consumes about 10 kilowatts. If you wanted to scale this to 322 terabytes a second, which is the actual need, it would actually consume 700 kilowatts, which is kind of impractical. So it's kind of difficult to scale and both satisfy the demand because of the power constraints that this kind of system would impose on the data center. Let's look at nanoelectronic circuitry, like how is this going to help us? So if you look at classical transistor scaling, this is the projected trend, like sort of the projected trend of how gate lengths will shrink and how the supply should shrink and how the threshold should shrink. And if you look at it, it looks pretty linear. But actual reality, it starts to taper off, and a lot of this is because of the leakage that's present in transistors. So a lot of the leakage in gate oxides and when you get to the nanoscale, the tunneling effects actually prevent you from actually doing the classical scaling, which then hurts you because you're not going to get the power savings that you would think that you would get by just scaling to a smaller, finer feature. The other thing that has been the trend, I mean, I used to work at Intel a long time ago, and the trend in general for saving power is to go to a lower node, and basically it gives you reduced capacitance, which gives you reduced power because power goes as CV squared F. That is only true for dynamic power dissipation. So if you predicted dynamic power dissipation should keep going down as you scale the CMOS size, but that does not happen. And the reason that does not happen is right about at 90 nanometer, the oxide gets so thin that a transistor that is sitting in its off state and not switching actually consumes more power than the transistor that is switching, because the leakage current through transistors becomes the problem. Because even if you had 1 nanoamp per gate, and if you had 1 billion gates, you have 1 amp leakage. So it starts to become a real issue as you start having more transistors and you start getting thinner oxides. So there's a lot of research going on how to actually make this better. There is another issue, which is how do you actually take the data off the chip? So if you look at the ITRS roadmap, which is the semiconductor roadmap that is used by industry for projections, the limit of the ITRS roadmap is 4096, which is, if you look at the bandwidth per port, if you want 200 gigabytes per second, you need about 4096, provided you have 25 gigabit links. Now, if you have only 10 gigabit links, you would need 10,000 pins, which is completely impractical. And if you need to scale to 400 gigabytes a second, you would need 8,192 pins, which is practically impossible. But if you look at an optical network, by scaling the number of wavelengths and keeping the fibers fairly basically constant, the power consumption basically doesn't increase very much, and you get the data rate that you want. So this is sort of the right sort of approach in terms of trying to scale for data centers. So what we've been trying to do is trying to see if you can actually integrate electronics and photonics and try to get optical switching to actually solve this kind of bandwidth issue. So the current generation, which is basically MEMS-based, is a little bit slow, so you need something that's faster. If you use an SOA or a semiconductor optical amp as the basis of your switch fabric, it also dissipates power because it's being actively driven. And it's fast, but it wastes power. So we are trying to see if we can actually integrate CMOS electronics with hybrid silicon photonics that John's group actually does, and in conjunction with Orion, which is a company that we work with, which is local, to see if we can actually do better. So our goal is to basically design circuits that can actually do fast optical packet switching and also demonstrate that we can actually switch a packet. And this is in collaboration with Orion, and this is ongoing work. So the idea basically is to have the photonics and the electronics close together. Why do you want this? Because a lot of the power is actually dissipated in the wire as it switches. So you want to keep the wire short to actually save power. So this is the architecture that we proposed, which is basically, here is an optical to electrical conversion. You basically bring into digital data, figure out what the data is, you route the configuration, and then you set up the fabric to basically route the packet. That's basically all that it does. So the optical switch was designed by John's group, and this is a optical switch that's based on a field effect, so it doesn't actually consume current. So it's actually a reverse bias diode, so it actually does not actually actively consume current. It's a hybrid silicon Mach-Zehnder modulator. So this was done by one of John's students, and this is sort of what we based our entire design on. So here is a optical switch, the previous one that we just talked about, being driven by electronics that was designed in my group. So we basically showed that yes, you can actually design a chip that drives the optical modulator and gets the right response. And then we did some power comparisons. So if you basically take all of the components that you need to make this fabric work, and you scale it from, say, 2 channels to 36, and the reason we went up to 36 is so that we could compare it to the existing electronic 36 by 36 switch that's available. The power basically goes to 7 watts, whereas the commercial electronic switching is 85 watts. So there's a huge gain in actually doing optical switching. And most of this power, actually, a large part of the 7 watts is also the FPGA. So if you actually make this also part of your CMOS circuits and sort of more optimized, you would actually dissipate less power, because an FPGA is a general purpose device and it's not necessarily designed to be power optimized. And if you optimize this, you can actually save a little bit more power in that section. The other thing that you can also do by putting electronics and photonics together is photonics, unlike electronics, is not as mature. So you're going to get lot-to-lot variation. You're going to get variation due to fabrication changes. You may want to like change the wavelength or change the on-the-fly sort of control the wavelength selectivity. For all of these things, it's better to have electronics that does the control. So it sort of removes a lot of this kind of errors that you get during fabrication. So if you could put photonics and electronics together, then you could actually get away with a less strict design rule, basically. And one thing that we tried to do was we wanted to basically keep the gain of the SOA, which is a semiconductor optical amplifier, constant no matter what the incoming power was. So no matter what the incoming optical power is, you basically regulate it so that the output optical power is a constant. And we designed a chip that actually looks at the power, and basically we use a transimpedance amp that looks at the input power and then correspondingly switches the drive current to actually control the output optical power. And we were able to show that with this kind of equalization, you can get a pretty good low error recovery of the data. So I'm going to switch gears a little bit and talk to you about how actual electronic photonic integration is done. Before I go into what we do, I'll give you a little bit of a sort of an overview of what actually is being done currently, and then talk about our work, and we'll conclude with some future work. So first of all, what is it that we can achieve if you do this kind of integration? One thing that we, like I just talked about, is the control and stabilization of the photonics, right? So you want to be able to design photonics with less stringent rules, but use the CMOS to sort of correct a lot of the errors, like have on-chip heaters, have some sort of feedback mechanism, do a lot of regulation, that kind of stuff. We're also working on advanced architectures which actually help you sort of have this intimate integration at the RF frequency prevents you from needing to do what is called matched design, which is like a 50 ohm termination, so they don't have reflections. So that actually saves power. You can also distribute the driver so you can actually get better modulation characteristics because you get a better gain through the system. So these are the kind of things that we're trying to work on. So this is the state of the art that's commercially available. This is called front end of the line integration, by which I'll tell you what front end actually means. So it basically has modulators, flip chip bonded lasers, optical fibers, and full receive path. And here's your fiber that plugs in. And this is commercially available. And this is a prototype from Luxtera. So Luxtera basically is a company that integrates CMOS and photonics together, and that's their entire product line. So the way they do it is they take silicon photonic circuits like waveguides, couplers, modulators, photodetectors, and add it to the standard CMOS flow, and then they actually make a fully integrated circuit which contains both photonics and electronics. So the way they do it is they make all their devices on a standard CMOS line, which means that you start at the transistor level and you start adding implants that are necessary for photonics, like germanium. And so you can make transistors, waveguides, phase modulators, and photodetectors. So these are the key components that they've actually been able to integrate into the flow. But there are limitations. One is the development cost is very high, as it is a very complicated process with a button, like, I mean, it has 30 masks, and on top of that, you're adding photonics into the picture, your yield is going to go down. And the other thing is, every time you change the CMOS node, let's say you go from like 90 nanometer to like 65 nanometers, you have to redesign your entire photonic process. So you actually do not leverage the latest advance in CMOS. So you're not decoupled. Your CMOS and photonics are not decoupled with each other. So you have to keep in pace, basically, which makes it very difficult. So what we try to do is a little bit different. First of all, photonics and electronics have entirely different length scales. Photonics in the order of millimeters, electronics in terms of microns. So you really don't want a intimate integration of the front end of the line. It's better to do it at the back end. And if you do it at the back end, then you can develop two processes in parallel and then join them at the end. So that's the kind of approach that we're taking. There are disadvantages. You might get slightly larger package size, and maybe there'll be a problem with waveguides if you're not too careful. But we've sort of overcome that issue. So the idea basically is that you basically have a photonics wafer or hybrid 3-5 silicon photonics wafer. You get your CMOS foundry die. You basically slot in the slots, drop in your chip, and then wire it and connect everything together and planarize it. So here's sort of like an example of the process. So we start off with a photonic IC. We make a hole that fits the electronic IC perfectly. We use what is called a self-masking process. And then we sort of put it together in a flow that sort of intimately integrates the photonics and electronics together on the same plane. So once it's very planar, you can just basically use standard optical lithography and start wiring it. Here it's like you can get wire densities down to 5 microns, and this is just limited by our current lithography, and we can actually go better if we need to. Here's an example of a CMOS die within a photonic die. This photonic die is from Ariane, and we basically measured the characteristics of the SOA before and after integration to show you that it works. And as a last slide, this process is very versatile. Not only will it support CMOS, it'll also support gallium arsenide. So one of the examples that I showed you of driving this Mach-Zehnder modulator requires high voltages and very high speeds. I don't know what I did. Therefore, you can't really use CMOS at that kind of, this is like 40 gigahertz, 25 gigahertz kind of design with 7 volts. So if you're going to do that kind of stuff, it's much better to use gallium arsenide, which has its own like processing challenges. But the way the process is developed, you can either use gallium arsenide or silicon, and it doesn't really matter. And that's the advantage of using an approach like this. You can put multiple die with different technologies all together and wire them up in a single package and have short wires, which saves power. The future work that we're working on is to basically continue this and actually show a full demonstration, which we hope to show shortly. So ultimately, the message I want to convey is that there is plenty of power savings to be had, and that have very tremendous impact on data centers, especially using photonic interconnect, and this seems to be the most promising way to go about it. And if you actually put CMOS and photonics together, the next generation of photonic devices will be much more efficient. I wouldn't have been able to do any of this without Professor Bowers' help, and also help from Ariane, Greg, Alex, and Eric. My graduate students obviously do all the work. I'm just the front man. I just say the words. They actually do everything. Everybody knows this. And the funding came from DARPA E5, which stands for Electronic Photonic Integration, and IARPA, which funded some of the initial work on the fabric switching network. Thank you.